All right, we're here to talk about Gauss's law with cylindrical geometry. So let's go ahead and get going. I'm going to start with a cylindrical insulator. So let's say we have a cylindrical insulator. Now, what I want to point out is that for Gauss's law, you know that that flow looks like this. You say my flux, my electric flux, is equal to the integral over a closed surface, field strength, dot dA. That's equal to the charge inside the closed surface over epsilon naught. And you say, hey, if I want to use Gauss's law, while it's always true, I know that when I when I choose a closed surface, you say I want to choose my closed surface in a way so that the E field passes through the point where I'm trying to find the field strength, and it encloses some charge. But it's important that I choose a boundary that's easy to calculate. All right, so I can calculate that surface area of it and do the calculation. Well, the problem is, if I have a conductor that is a cylinder, right? So there's my little cylinder. I'll draw like the axis of the cylinder here, right? That coming out the other side, right? Well, say this is all full of positive charge, uniformly distributed. Then my electric field for this thing, it's going to radiate out. The problem is, when I go to figure out the field kind of off-center, I know that I've got more charge on one side than the other, so it's going to direct the field line to be angled. And as I head further out, I'm going to be more and more off-center, and my field is going to tilt more and more. I'm going to end up with this kind of curve. And so, and then of course we'll have symmetry here, right? I don't know that I drew that well, but you get the idea. And so the problem is, when I go to draw a Gaussian surface for this, and I want to draw it in a way that's going to be easy to do the calculation, and so it'd be swell if the cosine theta from that dot product was, always the same angle, all right? So it'd be constant, and it'll pop out of the integral. And it'd be swell if the E field was a constant strength, it would pop out of the integral. He said, can I draw a boundary like that? Well, maybe I want to make it so that this cosine theta is cosine 90, say. Then this is going to have to curve so that it hits the E field lines at right angles or something. I'm going to end up with this weird shape. And if I, remember this is coming out all directions in 3D, if I rotate this, that's what it would look like. You say, well, am I going to be able to calculate the surface area of that weird shape, whatever that is? And not really, right? I don't know how to calculate the surface area of that. So this calculation, well, I can write a true statement. I'm not going to be able to do the actual calculation easily, and that's frustrating. So what we're going to do is we're going to actually just limit the cases we look at for this course. Okay, something like this is what they say, beyond the scope of this course. And so we will only deal with simpler cases. How can we simplify this? Well, instead of dealing with a cylinder like this, we're going to say, what would happen if we extended the cylinder, made it longer, and then I'm trying to find the field here? Well, my charge here would be balanced out by the charge here, and that little bit of extra charge would be just a little bit further over them. The axis is on this side, it's not balanced on this side because I'm off center. Yeah, but that's really far away. So the horizontal forces will almost balance. If I make it even longer, that the field, all this charge here pushing on a hypothetical positive here, the force from all this will be balanced by the force from all this, and the excess is just this little bit way over here. And so the point is, as I make this cylinder longer and longer and longer, the field lines will get straighter and straighter and straighter. The point where the field lines would end up being nice and parallel to each other is when the cylinder is infinitely long. And so we'll actually only do these calculations for infinitely long cylinders, because that'll make the field nice and simple. Right? So we're only going to work with an infinitely long cylinder. So I'm going to sketch that over here. Say that this is my charged cylinder, right? And I'm going to have this thing be infinitely long, right? Whoops. Infinitely long. So I'm just showing a chunk out of it, right? The cylinder really extends on out, heading out to infinity. So this kind of goes out to infinity, you know what I'm saying? In both directions. I'm just showing a chunk out of it. All right, so in this case then, here, we'll draw that axis down the center. It makes it easier for me to visualize it anyway, right? And it's going to kind of come punching out the other side. There we go. All right, so my art needs a little bit of work. It really ought to be kind of right in the middle. Am I going to draw it over again? I think I just did the same thing. Well, anyway, you get the idea. So we're going to say that this is full of charge. And hypothetically, we draw it as a positive. Sure, why not? I mean, it could be a negative, and the field lines will go the other way. It's okay. Draw it as positive. So let's say we have, let's see here. So for our first example here, all right, example 1, we'll say that we have, and now I could say it's infinitely long. But a lot of times in AP Physics, they'll just say that it's very long. And you'll say, okay, I'll approximate it as being infinite, all right? We'll say this is a cylinder of radius r, okay? So here, look, that's r. If you want a cylinder of radius r, containing a uniformly distributed charge, distributed charge. Now, I want to say the charge is evenly distributed in this. Now, because this is an infinite cylinder, I can't say how much charge is in it, because if it's infinitely long, even distribution, it'll have an infinite amount of charge. So what I'm going to do instead is I'm just going to talk about my charge density, okay? So for this guy, I could talk about charge per volume, like we did with the charged sphere, if I wanted to. But this geometry actually lets me get away with doing it another way. I could, instead of talking about charge per volume, although I could do it that way, we could talk about charge per length. Like, if my charge is evenly distributed, if I take a chunk out here and a chunk out here or a chunk out here, same size chunks would have the same amount of charge in them. I can talk about how much charge I have, per meter of length that I chop out of this thing, right? And so that'll be called my linear charge density. So it's uniformly distributed charge with a linear charge density and I'm going to use like a Greek letter L for this, lambda. Okay? So I'm telling you the charge is evenly distributed, and I'm telling you the set value is my charge per meter of length, coulombs per meter. All right, having said that, what do we want to find in this case? Let's find the electric field strength outside the cylinder. Find E at R greater than R. Okay, so outside the cylinder. That'll be first case. We'll come back and do inside the cylinder for our second case. So maybe, like out here, some distance out here, right there, how strong is the electric field at that point? At little r, some distance bigger than bigger, so it's outside, right? Now, it'll help if I also draw an end-on view. So I'm going to draw an end-on view of the cylinder, like this. So here's a cross-section of my cylinder with a radius r. And I'm trying to find my E field outside the cylinder, right? So, I don't know, some distance out here, there, right there, okay, at little r out. Okay, find the field there. Okay, so if we do that, I just realized a good reason why I don't want to make that diagram right there, but that's okay. So there we go. So what we want to do is we want to figure out our Gaussian surface. Now, part of drawing it is to try to make this calculation easier. It'll be easier to see what I'm doing if I draw the E field line. So I can figure out how I want to make my boundary of my Gaussian surface. So let's draw the E field in. Now, I know that right in the middle, it of course is going to radiate out. We drew this diagram before. But now that it's infinitely long, if I come off center a little bit, if I'm just a little bit to the right of center, and so the extra charge on the left is like way out there. And if it was in fact infinitely long, the excess charge is an infinite distance away. And so it balances out. We're just going to have a nice the field lines will look uniform in the plane of the page, right? My E field. But, right, whoops. So I'm trying to draw these evenly spaced. On the plane page, it appears that way. If I look from the end, though, I can see that my field lines are going to radiate outward, but they're going to get more spread out as I go farther away. All right. Now, I don't have a real great way of illustrating that in this picture. That's okay. So my field lines are actually getting more spread out as I go farther away. All right, so let's find the E field out here at R. This is little r away. You say, so what shape boundary do I want to do for my Gauss's law? What shape surface do I want? I'd like to do something to make that cosine theta be a constant. So it'd be great if I could make that be, I need to enclose some charge inside. So I need my boundary to kind of go around here, right? Kind of like we would if this was a sphere. Yeah, we want to do that boundary. In this picture, it's going to look like a circle. Right? But when I come out here, right, there's my circle around. What shape am I going to have? You say, well, I need to enclose this charge. I think you can see it's going to be a cylinder, right? It'll be this cylindrical shaped bubble, right? Gaussian surface. Now, here's the problem. How long is my bubble? And you say, well, if I wanted to enclose all the charge, it would go out to infinity. And that's a problem, all right? That's a problem. So what we're going to do, well, why is it a problem to have it be infinite? Because if it was an infinitely long bubble, it would have an infinite area, and it would contain an infinite amount of charge, and this would cause problems with doing any kind of a calculation with it. So what I'm going to end up doing, what's infinity over infinity? I don't know, ask your math teacher. Anyway, but the point is, we're not going to do that. Fortunately, we don't have to make it infinite. Here's what we're going to do. That cylindrical bubble that's going to go around this, we're just going to choose to make that bubble. It's going to pass through this point E, point here where we're trying to find the E field strength. We're going to make it nice and symmetric here. This is meant to be the same distance out, okay? I'm just going to make a bubble that big. How big, you say? Here it is enclosing, going around the cylinder. And back here. Cylinder. How long is this? I'm choosing to make a bubble that has a length, I'm just going to call it L. Right? This is just an arbitrary length I'm choosing. Just saying, oh, let's just make it this long. All right? Now, this is a value that wasn't given in the problem, this length. It's something I'm making up. And so it's something that you would certainly hope would drop out in the end in the calculation. And it will. All right, so it'll be fine. Okay, just bear with us for a while here. It'll all work out. So now I have this closed surface. I have to have a closed surface. It has some charge inside it. I'm following the rules for Gauss's law. Okay, and so I want to go ahead and do my calculation. All right, now I like to work under my equation, but I wrote this too far over here. So I made my diagram too big. So I'm just going to shift this over, all right? So here we go. Now, my electric flux, integral over closed surface, E dot dA, equal to the charge inside over epsilon naught. You always write the formula before you do the calculation, right? Okay. Anyway, it's a good thing. It's a good thing. So here's my calculation. Now, what I want to point out is, this is saying I'm adding up my E dot dA over that whole closed surface. What I'm going to say is, I'm going to split this closed surface into 3 parts. When I talk about all my flux that comes out the left end of the cylinder, the flux that comes out the curved side of this cylinder, talking about the Gaussian surface that punches out this curved cylindrical surface, and the flux coming out the right end. So I'm going to kind of split this flux up into 3 chunks. The flux out the left end, plus the flux out like the side of the cylinder, that curved side. Of the Gaussian cylinder. And then my flux, electric flux out the right end. Okay? And that's going to, all right. So here we go. Get my total flux. Now the good news is, when you look at the diagram, you see the way the field lines are going. You say, how much flux is punching in or out of this left side, this flat surface here of my blue cylinder, of my Gaussian cylinder, Gaussian surface? You say, there's nothing going in or out. The field lines are just skimming the surface. There's nothing going in or out, crossing the boundary. So I actually have no flux at this end. Same thing happens at this end, right? The field lines, E field lines are going up and down, right? Nothing is punching through the surface either way. So actually, both of these terms are going to be 0. There's no flux at those ends. I just have to add up all the flux going through this curved side of the cylinder, right? Another way of looking at it, if I did the math on this term for these sides, I would do my integral E dot dA, right? And so I'd have a dot product there. That would be a cosine theta, looking at the angle between the E field line and the area vector. Which way does an area vector go? It always points perpendicular to the surface, straight out. So on this right side, my area vector would be going this way. My little area vector is like all over that surface, right? It would all be pointing that way. Over here, my area vectors would all be pointing that way, pointing out of the left end of the cylinder, right? These are all my little DAs. For this round part, it's easier to draw here, but my area vectors would all be going this way. You see, now look, I can see that on this surface here, right? All over this surface, the E field is parallel to the area vector, parallel to the area vector. Like I said, I can see it better here on this diagram. My area vector is pointing out of my bubble, right? But on the ends, look at this angle. Between the E field line and the area vector, that's 90 degrees. 90 degrees, right? And so if the angle cosine of 90 is 0, I get 0 flux out both sides. It works mathematically from the cosine also. All right, so the only flux is out the sides. So how do I calculate that? Let's do the E dot dA for that flux out the side. So when I do that, you say, so I'm really just worrying about this term here. Okay. Q in over epsilon naught, right? You say, hey, what's this term here going to be for the flux to the side? Well, cosine theta, we just figured out that for this curved side here that you see pictured here, the area vectors all point straight out and the E field points straight out. They're going parallel to each other. So I'm going to get cosine of 0 degrees everywhere on this surface, okay, on this curved bubble, right, the surface of the bubble, the sides of the cylinder. I'm going to get cosine of 90. That's a constant, so it'll move out of the integral. The E field strength, everywhere on this surface, it looks like this. By symmetry, it should be the same strength field all the way around. My spacing, my field lines really ought to be the same all the way around on that surface of the bubble. You know, it just makes sense, but because of the symmetry here, equidistant out in all directions, going to be same strength field. So that E is a constant, so it can factor out of the integral. So I'm going to have E times the cosine of 0 degrees factor out. I just have this now, adding up the surface area for this surface. Okay, what is the area of that surface? Well, imagine, if you will, that here is my charged cylinder, and here is that Gaussian surface, right, that I'm wrapping around it, right? I'm trying to find my electric field strength at some point out here, right? Some point out here, a distance away from that cylinder. So I make this bubble around the charged cylinder, right? What I'm gonna do is I'm gonna cut that down the side. I'm gonna slit it down the side and unroll it. What shape is that cylinder now? And you say, yeah, that cylinder, it's now a rectangle, isn't it? how long is this? That's that length L that I chose to make it. And how long is this? That's the distance all the way around. Yeah. That's just the distance around. That's the circumference. That's this distance around here, which is a circle with a radius r. So what I'm doing is when I go to find that area, I'm just going to go ahead, I'm going to take this guy, I'm going to take that Gaussian surface, slit it along the side, and unroll. And when I unroll it, that Gaussian surface will be a rectangle. This is that L that I chose. This is 2 pi r, the circumference around. So that area is just going to be 2 pi r times L, the rectangle, length times width. Okay, cosine 0 is just 1, so it's just E times 2 pi r L. That's equal to the charge in over epsilon naught. So now I just have to figure out, that's the left side, all good. Now I just have to figure out the right side. I have to figure out what's the charge that's inside my bubble here. All right? So the way we're going to figure that out is to say, again, we're doing a finite bubble. It's not infinitely long, so I'm not going to have an infinite amount of charge in. There's a certain amount of charge in this chunk that I'm like slicing out of the rod, out of the cylinder, right? And so you say, okay, what's the charge in there? Well, I didn't give the Q, but I gave you the linear charge density, lambda. You say, so what's that? Well, I'm going to diagram it here. Lambda is my charge per length. Yeah. So let me write it like this. Charge per length. So in this case, it'll be the Q inside the bubble to the length of the bubble for the Gaussian surface. That's this cursive L. So it'll be Qn to L. So rearranging, what's Qn? Oh, that's just lambda L. And so that's what goes in there for Qn, lambda L. And I still have that over epsilon naught hanging around. Okay, what's going to happen here? See the little L there and the little L there? Going to divide both sides by little L, goes away. And that's awesome because that variable, that L, that's just something I chose. I just arbitrarily said, hey, let's do a slice this long, right, for my Gaussian surface. So bam, bam. Feels real good to see that go. 2 pi r comes the other side. And my final answer here is that my E field strength is going to be lambda over 2 pi epsilon naught. And this r in the denominator, I'm going to bring it out there. These are all nice constants. I can see my E field is proportional to 1 over the distance. All right? So that's my answer. All right? Now, could I write this in terms of like 1 over 4 pi epsilon naught, so just use the Coulomb's law K, if I wanted to. If I did it in terms of Coulomb's K, K is 1 over 4 pi epsilon naught. So to get another 2 on the bottom or another 2 on top, it would be, I don't know, K times 2K lambda over R. Yeah, 2K lambda, yeah. Yep. Okay, that's what I would get. 2K lambda times 1 over R would be E. If I want to do it in terms of the Coulomb's law K, who wants to do it in terms of the Coulomb's K? Okay, no. Epsilon naught is cooler. It's that universal constant. All right, so anyway, so there you go. Okay, what I want to point out here, last comment about this particular problem, and that is, notice that when I have charge, I'm just going to say that spread out in cylindrical geometry, or in like a line, or like maybe like a charged wire or something, if the charge is spread evenly along it, from along an infinite wire, the field strength is going to drop off proportional to 1 over R every time. Okay. If I have a point charge, then it spreads out evenly in all directions in 3D. It makes like kind of a sphere, expanding sphere. This is going to be like an expanding cylinder as it spreads out. So my field strength drops off as 1 over R when I have linear or like cylindrical geometry. When I have spherical geometry, it's 1 over R squared. Okay, that's kind of worth knowing. We will deal more with cylindrical geometry when we talk about wires and like current flowing along wires coming up. And we'll talk about when we do magnetism, magnetic fields from charge flowing down wires. Then we'll deal with this 1/r symmetry a lot. So anyway, for cylindrical symmetry. Okay, so that's that. Okay, so we just solved this problem, finding electric field outside an infinitely long charged insulating cylinder. Okay. Yes, and I should have made that clear. This is an insulator, right? You kind of knew because I colored it in orange. And you say because the charge is uniformly distributed, if it had been a conductor, where would the charge have been? At the surface, right? And so this instead was spread throughout. Let's do another case. So we're going to do the other case. That's going to be just like this, but now we're trying to find the field where? Inside. So I want to find the field at little r less than big R. Okay, am I going to draw all over my old problem on top of it? Or am I going to make a new diagram over there and rotate the camera? What do you think? I think I'm going to rotate the camera and use the other board. Okay. So here we go. Well, you know what the problem is with doing this? I can't tell where the edge of my field of view is. All right. I think I did that well, so you can see the entire board. We shall find out, and I'll be really mad when I find out that I went off the edge, but that's okay. So here we go. We're going to do case 2. Okay, this will be same as 1, except find E at R less than R, so inside the cylinder. Okay. So here we go. Oh, okay, so here's like the end-on view of the cylinder, and here's like a side view of the cylinder. Why did I make that so small? I'm worried about going out of your field of view, that's why. Oh, look at that. That's nice. That's nice. All right. Draw my axis for the cylinder because it helps me visualize this. Radius big R. Radius big R. Good enough. Okay, we want to find the field strength this time here, right there. That's inside. That's at a distance, little r, smaller than big R. So I'm inside the cylinder. Then I'm trying to find right there, how big is the E field? Little r less than big R. How am I going to do this? Well, again, it helps to visualize what's going on if you draw the field lines in. For this infinite cylinder, right, this cylinder continues on in both directions. Okay, this is not a finite cylinder, it's an infinite length cylinder, okay? I'm just not drawing it. All right, here we go. So, here we go. Well, once again, you know that it's important when I choose my Gaussian surface, that I choose one that I can easily do that integral for Gauss's law with. So once again, we're going to go ahead and we're going to do something that looks like a, ooh, that was terrible. Looks like a circle here. Here, when I extend that along, it's going to be a cylinder. How long am I going to make the cylinder? I'm not going to make it infinitely long because then I have infinite charge inside and infinite surface area and it causes problems. So I'm going to draw my cylinder just some arbitrary length L. Okay, or it just could be any length. I'm just going to choose to make my Gaussian surface have a length that I'm going to call L. Okay. So my Gaussian surface is a cylinder of length L and radius little r. All right, here we go, running through. Once again, I've got flux left end, right end, and the side of the cylinder. I'm going to add up the fluxes going through. So we're going to do this. We're going to say my electric flux, total flux, is going to be equal to, fine, we'll write the full formula down. Integral of closed surface, E dot dA is equal to the charge inside over epsilon naught. And so this is going to be the flux out the left end plus the flux out the sides of the cylinder plus the flux out the right end. Okay. And we know that there's no field lines crossing going in, out or in this end. There's no flux going in or out this end. I know that the fluxes are going to be 0 for those. I just have to worry about flux coming out this curved side here, the main side of the cylinder. That's the only part that I care about. And so my flux is just going to be that for the left end, and that's just going to be an integral E dot dA. Now it makes logical sense to me that my area vector points always straight out of the surface, and the E field lines will be going nice and parallel to it. That's going to happen everywhere on this surface. The E field lines will be nice and parallel to my area vectors, yeah? And so this is going to be, for this surface, it'll be a cosine of 0 degrees, which is just 1. For these guys, I got a cosine of 90 degrees, which is 0, right? For these guys, cosine of 90 degrees, which is 0, right? Between the area vector shooting out of the bubble and the E field going parallel to the bubble on these sides, right? All right. My E field is going to be, so these sides I don't have to worry about anymore. This side, the E field is the same strength everywhere around there by symmetry. If I had drawn this centered, drawn a nice circle, sorry about that. The E field would be the same strength everywhere out there, same distance from the middle. So the E is a constant and it can factor out, constants factor out of the integral. What's left? Integral over a closed surface dA. Yeah. On the right side, we got Q in over epsilon naught. So you say, okay, hey, what is that integral dA? You say, that's just the area of the side. Remember what we're going to do. We're going to take this side, take this guy, right, that Gaussian bubble, and we're going to slip down the side along its length and unroll. And that's going to give us a rectangle where this will be that arbitrary length L, and this will be the circumference 2 pi little r, right? There's a radius of little r here. It's a distance around that circle, which means this area is 2 pi r L. This is exactly, yes, this is exactly like what we just did in the previous problem, I agree. Okay, moving onward. The right side now, this is the tricky part. We've got to figure out what the charge is inside our bubble. Now before, we just talked about charge per length, lambda. And we said, oh, okay, so lambda is charge per length. The charge inside is just lambda L. The problem is I don't have all of that charge that's in that length. This charge out here, right? There's all this charge that's out here, outside the bubble. That doesn't count. I just want the charge that's inside my bubble. So how do I get rid of it? I just want to take the fraction of the charge that's inside. Now, in this problem, we were told that the charge is uniformly distributed. So, it means it's going to be easy. It means I can just take a ratio. I can say, hey, if this area of this cross-section is half of the total area, which this one isn't, but if it was, it would contain half the charge. If this was, or we talk about volume, if this chunk was half the volume of the whole chunk from here to here. So I'm just talking about like from here to here for length L. If I look at all the charge in there, this volume is some fraction inside the bubble, right? And so I just take the ratio of these areas the same as the ratio of the volumes, right, for that same chunk. And so that's what I can do. So I'm going to set up a ratio. I'm going to say my Q, and I sure hope this is in the range of field of that camera. Q in is to the total charge. Now this is total charge in length L. You know what I mean? In just the total charge, just in this part, from here to here. Okay? That ratio will be the same as the volume that's in the bubble to the volume that's just in length L. Right? The volume contained in length L. You know what I mean? The volume, you get it. Volume in length L. So here we go. So if I do this, rearranging, I'm going to get that Q in, which is what I need for my Coulomb's Gauss's law. Move this Q toe times volume over total. Now what's the volume in my bubble? Well, the volume of this bubble, right? You know how to find the volume of a cylinder, right? You take that cross-sectional area times the length. It's like I'm taking a circle and I'm sweeping it in 3D through this. It's the area times the length. So it'll be the bubble, the Gaussian surface, the volume of the Gaussian surface is pi r squared L. What's the volume of the whole orange cylinder from here to here? Well, the cross-sectional area times the length. The cross-sectional area of this circle is pi big R squared, right? Times L. All right? Now this is great, except I don't know what that total charge in that chunk is. But I can get it from the lambda. All right? So we remember, I'm going to go ahead and use this space. Use this space. We know that lambda is the charge per length, right? And so in this case, the charge for that length, for that L length, per length L. So rearranging, lambda L will be the charge contained in that length L. So lambda L goes in for Q toe. What's going to happen here? You can see that this pi, L cancel out on that side. So it's just going to be lambda L times R squared over big R squared. Okay, and that's the Q in my bubble. The Q in the bubble, in the Gaussian surface. This goes into Gauss's law. All right, so that's the tricky part. Okay, but again, because it's evenly distributed, we can just set up a nice ratio. Okay, so if I do this and I put this in there, lambda L R squared over big R squared, and take a look, here we go, here's our final equation. Look, you see that L there and that L there? They're going to drop. I've got no more little L's in my calculation, which is awesome, because that's a variable that I made up. I need it to not be in my answer. So that's great that that drops out for us. Bam, bam. Okay. So rearranging. I'm just going to do it all blue. Okay. So I'm going to get an E field. Remove the 2 pi r to the denominator there. Hey, this r and that r squared. See what's going to happen, right? This will cancel one of those r's, so the r squared goes away. So I'm going to get an answer. It'll be lambda 2 pi epsilon naught, right? There's a big R squared in the bottom still, but, right? And that's my final answer here. Could we rewrite it in terms of Coulomb's law K if we wanted to? Yeah, we could. But I'm just going to leave it in terms of epsilon naught. So that's what we're getting, okay? Notice that for this case, inside, right? Inside the cylinder, here's a bunch of constants, but my E field is proportional to R. So that's a direct relationship when I'm inside the cylinder. When I'm outside, we got a 1 over R relationship. Okay. If I, here we go, if I made a graph, because everybody loves graphs, here's my cross-section of that cylinder. I'm going to make a graph of E field versus distance out from the middle of the cylinder. So here we go. E field strength, this is going to be R, my distance out from the middle. Here's 0. Here, right here, that's big R. What does this graph look like for this case? We say, well, when I'm inside, it's proportional. What happens if R is 0? E is 0, right? So my graph is going to start from here, and it's going to be linear, right? What about once I'm outside? When I'm outside, it's proportional to 1 over R. So we're going to have a 1 over R curve. And proportional to R on the inside. Okay. Could we verify that that peak, that those match up and meet up perfectly? Yeah, we could. Here I've got lambda over 2 pi epsilon naught 1 over R. My R here is big R, so I would get lambda over 2 pi epsilon naught big R for the calculation for the field strength outside. Lambda over 2 pi epsilon naught big R. Okay, for that value right there. Let's check the other equation. If I put R as big R in here, that'll cancel one of those. I'll get lambda over 2 pi epsilon big R. Hey, I get the same answer. They do match up perfectly, those two equations, stitched together perfectly right there at the boundary. Yeah, it's an undefined right there. It's not undefined. It's not undefined. It's the same value for both functions. Yeah. You just, overall, we have to do it piecewise as two separate functions. But they do stitch together nicely there. Okay, there we go. That's, all right, so that is finding electric field strength for cylindrical geometry for insulators where it's uniformly distributed charge. What would come next? We would do a case for an insulator where the charge is not evenly distributed in the cylinder. Maybe that charge, it kind of makes sense that light charge would tend to repel. Maybe the charge gets more densely packed as we head to the surface of the cylinder. We should do a case like that now, okay? And yes, you know that we're going to do the same Gaussian surfaces we did before. We'll do cylinders, right? Outside, going to look the same. Inside, going to be trickier, okay? Going to be a little trickier inside because it's not going to be, if I have half the cross-sectional area, I'm not going to have half the charge because it's less densely packed here and more densely packed out there. So it's going to be trickier. We're going to have to use calculus, the magic of calculus, and slice into a bunch of little DQs, right? And add up the charge that's inside the volume and all that jazz. Let's do that in another video, all right? So this is the intro to insulators that are cylindrically shaped. So E-fields with Gauss's law for cylindrical geometry, uniform charge distribution. We'll do non-uniform next video. All right, that's it.